Okay, good morning, ladies and gentlemen, and welcome to another video. Today we're going to discuss the chi-squared test of independence. And if you watched my video on the chi-squared test of homogeneity, I said several times that test is very similar to this test. In fact, the mechanics are identical. It's just a matter of really what question is being asked and how the sample is being collected. So that's basically what we're going to discuss today. I'm not going to go over every single detail, but I will touch upon. I'll go through an example. I'll show you the difference in terms of how the sample is collected. And then we will also talk about the idea of residuals when dealing with a chi-squared situation. Okay? But of course, before we do that, this video is brought to you by Couch Potato brand snack food and beverages. Please, folks, reminding you to wear a mask in public. However, be sure to remove that mask to ingest any of our snacks. Of course, also in the privacy of your own home when you remove that mask. All right, let's move on. So here is a situation. Take a moment to read. All right, so first of all, again, we have categorical data, or in other words, qualitative. We are dealing with counts in this case, which of course can be converted to proportions. So this is once again very similar to like a two proportion z-test, except we're expanding upon the two proportion z-test. And we are asking if there's an association between generation, so that categorical variable, the categorical variable of generation, and also party affiliation. So that is a second categorical variable. So we're dealing with two variables. They are generation and party affiliation. And we're asking the question, is there evidence of an association? So that phrase right there that I just highlighted in orange, that gives us a hint that we are going to do a chi-squared test of independence, or another way of saying that is a chi-squared test of association. All right. Another way to differentiate between chi-squared test of independence and chi-squared test of homogeneity is how the sample is being collected. So look how the sample is being collected here. What we're doing is we're simply taking a SRS of people, and each person that gets plucked out of the population that responds to this survey, they're being labeled, or they're answering questions and being identified in two different ways. In the sense of what generation are they from and what party affiliation do they prefer. Okay, let me go into a little bit more detail. So let's say this is the population of all people, and actually it's not really all people, it's only the population of boomers and millennials. So let's just say that it's just the boomers and millennials, right? So it's all of those people. But what we're doing is we're diving in there and we're just taking a random sample of 202 of these people, and we're asking each one, are you a boomer or a millennial? They answer. And we're also asking them, what is your party affiliation? And they'll answer. Right. And of course, we're making some simplifying assumptions. We're assuming that there are only these three party affiliations. Of course, that's not the case, but this is just for illustration purposes. So each person is being labeled as some sort of generation, and some sort of party affiliation. Now, how is that different from how we collected data on the previous example? Well, remember, from the previous example, what we did was we took the population of all graduating classes and we identified 3 subsets of this population that we're interested in. And we dove into those subsets and we sampled from the subsets themselves. We didn't just simply sample from the entire population. So that's the major difference. With the chi-square test of homogeneity, we are going to identify subsets that we're interested in. We will randomly sample from those subsets and then ask the people sampled a follow-up question to place them into the category of the second variable. However, with a chi-square test of independence, we simply dive into the entire population and survey people from the population and label each person with 2 variables. All right, so hopefully that makes sense. This happens to be the data that we obtained from this simple random sample. There were 202 people. You can check that out yourselves. Now, how do we state these hypotheses? So in the previous test, we assumed that the distribution of those categorical variables were homogeneous. In other words, they were all the same. And so in order for us to make a similar assumption here, we are going to say, we're going to assume that generation and political affiliation are independent. That is going to be the assumption that we carry out through this process. We are going to assume independence. And then what we're trying to do is see if there's evidence that there is an association. So we're going to try to prove or collect evidence that generation and political affiliation are dependent. Right, because independence is something that if we are able to prove independence, then that just means that these variables are not related to each other at all, and that's not very interesting. The whole point of trying to conduct some kind of a test is to try to link 2 variables together. So the onus is on us to try to disprove the null hypothesis and try to collect evidence to sort of see if we can support the claim that generation and political affiliation are indeed dependent on one another. So that's how we are going to state the hypotheses on this type of test. And once again, this is called a chi-squared test of independence. All right. Now, the conditions, again, I'll leave that up to you, but they are identical to the chi-square test of homogeneity. And again, if you've been sort of following along throughout the year, you probably have a pretty good sense as to what the conditions are. Now we're going to take our observed data. That information is important because, of course, we need to write in the total column and the total row. I don't know if you can tell, but that information wasn't given, so I had to write it. I don't know if you can tell that there's a difference between what I wrote and what was typed. But remember now, what are we doing? What are we assuming? How are we going to use that null hypothesis to calculate the expected? Well, remember, we are assuming that these 2 variables are independent. And what did that imply, or what does that imply about these 2 variables? Well, it implies that, for example, if we were to try to calculate the probability of being a boomer given that you're a Democrat, that should simply equal the probability of a boomer, right? That is the assumption we are making. We're assuming that is true. Now, it might not be exactly true in the data that we're observing, but again, that's sampling variability. Sampling variability might not necessarily show that this relationship is true exactly, but that is sampling variability for you. So what we have to do is just assume that this is the case. And the best estimate that we have for true proportion of boomers is exactly this total, or at least is taken from this total column here, right? We took all of the boomers, or all of the people that identified as boomers, 105 of them, divide by the total people that were surveyed, and this is our best estimate for the true proportion of boomers. So that's about 52%. So now what I'm going to do is I'm going to take that number, that 52%, I'm going to take the total number of Democrats, which was 84, and I'm going to multiply it by 52%, right? Because I should expect that 52% of Democrats are boomers, and I should expect that 48% of millennials, of Democrats are millennials, right? Because we are assuming independence of these variables. So as we move from Democrat to Republican to Green Party, the proportion of boomers should remain consistent. Again, assuming, because of the fact that we're assuming independence between these two variables. So I'm going to take a moment, pause this video, and fill out the expected table. 1 second. All right, and so here we have it. So in each category of political affiliation, there should be 52% boomer and 48% millennial, based on our null hypothesis. Next, we need to calculate the chi-squared values for each. So remember that each one of these cells is going to be the observed value minus the expected value squared, and then we divide by expected. Of course, we square that difference in the numerator because if we didn't do that, and then if we sum together all of the chi-squared values, we'd just get a sum of 0, which wouldn't tell us anything. I had a student ask me, why do we divide by expected? So I want to just give you a brief example as to why it's important to divide by expected. So give me 1 moment, and I'll set something up. All right, so let's say for a moment that we calculated the test statistic by just taking the sum of all of the observed minus the expecteds and then squaring them. In the situation here, we have an observed value of 105, but we expected 100. That's not really that far off, right? We observed 105, we expected 100. That's not really too bad. It's a difference of 5, not too bad. In this example over here, we observed 6, but we expected 1. That's pretty far off, right? You actually observed 6 times more than what you expected. Yet, there's still a difference of 5 between these observed and expected values. So the thing is, if we didn't divide by expected, now let's go ahead and take this number and divide by what was expected. Well, let's square it and then divide by expected. And then let's take this number, square it, and divide by expected. Here, you're going to get a chi-squared value of course, 25 over 100, which is 1/4. Whereas here, you're going to get a chi-squared value of 25. This makes sense. This makes more sense than just simply taking the difference, or just simply taking the difference and squaring, because a difference of 5 here is not very big because we expected 100, whereas a difference of 5 here is very big because we only expected 1, right? So by dividing by your expected value, it gives us a sense, it sort of grounds us to, I guess, to give us a fair assessment of what is actually going on. All right, so hopefully this sort of at least gives you some kind of understanding of why we divide by expected. Now, of course, what we're going to do is once we take all of our chi-squared values, we're going to sum them together to get our test statistic. So let me take a moment and do that. I forgot how to pause. There we go. So I just want to show you that what I decided to do was to use an Excel spreadsheet to fill out all of this information. I do strongly recommend you get used to using Microsoft Excel in one way or another. It will prove to be extremely valuable for you in probably most of the professions that you might end up getting into. Microsoft Excel is an extremely valuable tool, and many businesses use Excel. So I typed in the observed value. I set up a formula. You can see it up top here to calculate the expected, but it is exactly the formula that we discussed previously. But what I did was then I went ahead and I took my observed value of 36, subtracted the expected value of 43.6. I squared that, and then I divided by that expected of 43.6, and I got my chi-squared value. And I did that for each individual cell. It was just a lot quicker than doing it by hand. And there's no real easy way, unfortunately, of doing it on your calculator. So the TI-84 is not very useful when trying to find the individual chi-squared values for one of these tests. And of course, the sum of these values is your chi-squared test stat. All right, so that's 4.85 to calculate the p-value. So we place that somewhere along here. This is what we observed. To calculate the p-value, we're going to ask ourselves, what's the probability of getting a chi-squared value, which is greater than or equal to 4.85. And of course, degrees of freedom. We cannot forget degrees of freedom, because as the number of categories changes, or the number of possible values for each variable changes, then that means we'll be, adding more numbers together to get our chi-squared test stat. And the more numbers we add together, it changes sort of the meaning of what's a large chi-squared value and what's a small chi-squared value. So as I mentioned in the previous video, we're doing a chi-squared test of homogeneity or a chi-squared test of independence. We want to take the number of rows minus 1, so that's 2 minus 1, which is 1, times the number of columns minus 1, so that's 3 minus 1, which is 2. So in this situation, our degrees of freedom is going to be 2. I just want to show you that I did all this on the calculator as well. So this was my observed matrix. Okay, remember, matrices are read as, in terms of their dimensions, rows by columns. So there were 2 rows and 3 columns. So I just entered 2 by 3. I entered the observed data. And then if you go to stat tests, chi-squared test. Oops, I chose the wrong one. And then, if you choose the wrong one, you just go back to stat tests. So this, I'm just testing you by making this mistake, just to show you what not to do. All right, we select chi-squared test. Our observed matrix is matrix A. Matrix B for expected doesn't really matter. It's up to you though. Press calculate. Okay, you can see the chi-squared test stat is the same as what we had. You can see the degrees of freedom is 2, but the important thing, new information, is the p-value, which is 0.0884. All right, and let's say alpha was in this case 0.1. So in this case, our p-value is less than alpha, so we would actually reject H null. And we have evidence to support the claim that generation and political affiliation are dependent. So a follow-up question, as I mentioned in the previous video, might be something along the lines of which political affiliation value seems to differ the most among the two, the generational people, the people of the different generations. And so in order to answer a question like that, you would want to analyze the residuals of your chi-squared values. So let's go down here and we can create a table of residuals. Now the table of residuals, it simply takes the observed value from a particular cell, it subtracts the expected value from the corresponding cell. It doesn't square it. So now what this does it allows us to see whether we underestimated or overestimated based on just looking at the residuals. So it allows residuals to be negative. That piece of it, that information tells us, on which side was our estimation. And then of course we divide by not the expected, but we divide by the square root of expected. And we do that for each value. And there we have our residuals. Now, looking at this, it seems like the largest residual exists, or the largest two residuals really exist in the Democrat column. So there was a large discrepancy in the Democrat column with respect to the age groups. All right, so you might point to the Democrat column as being the one that really causes the largest discrepancy among the age groups, which I think is probably kind of true. So, but I'm not 100% positive about that. This data isn't exactly 100% up to date, let's say, but it would be interesting to see if we sort of ran this survey again, what would happen. All right, and just to finish off, I want to close with discussing, again, the residual. Remember, the residual is basically the chi-squared value. You take that value and take the square root of it. The one important thing is when you take the square root of when you take the radical of the numerator, you do have to take into account the sign. So we do want to allow the numerator to be either positive or negative. All right, so that's the major difference. All right, ladies and gentlemen, that is all. If you have any questions, feel free to email, and I hope you have a nice day. Take care. Bye.